So let's take this example and let's try to sort this example using selection sort. Meanwhile, we'll understand how selection sort works. So what I want to do now is I want to find the minimum element in this whole array. So this is 0, 1, 2, 3, 4. So I want to find the minimum element in this array. So that element occurs at the 4th index. So I'll find this element, I'll traverse the array, I'll find the minimum element, and I'll put it at the 0th index. So let's say I have a marker here. Let's call it I. So I'll search from I till n, and I'll find the minimum element, and I'll put that element at the ith position. So now I have 1, 4, 3, 2, 5. So the how we are going to put this element there, we'll just swap those two elements. The element that is present at the current location with the minimum element. So now this was the minimum element in the whole array. Now I have placed it at the right position. Now I want to find the second minimum element. So basically what we are trying to do is, let's say you want to sort this array. So how do you want, so like when you sort this array, how will your array look like? Minimum element, second minimum element, third minimum element, fourth minimum element, fifth minimum element, and sixth, and so on. So we found the minimum element, we placed it at the correct position. Now we are trying to find the second minimum element, we'll place it at the right position. So the second minimum element we'll find in this array. So basically we want to find this second minimum element from 1 to n, which means that we want to find the second minimum element, and we know that we have placed the minimum element at the first index. So we want to find the second minimum element from the array 2 to n. So we find the minimum element in this subarray, which is 2. We replace it with 4, and these two elements are sorted now for our array. 1, 2, 3, 4, 5. Somehow we have got this array sorted, but let's say if this subarray was not sorted, if it was still unsorted, what we'll do, we'll find the minimum, the third minimum element in this whole array, which will be the minimum element in this subarray. We'll find that minimum element and we'll place it at the third minimum element position. Does this make sense? With me till here?
Yes.
Is there anybody who did not understand this? Right. So I'll just write I'll quickly write the code for this. So let's say, so how we are going to do this is, Acha guys, I'll be giving you small hints while coding also. So there is a problem with declaring this variable. Can somebody quickly point out what the problem is? Sorting of single element will signify, basically what we are trying to do, Karan, is we are trying to sort this array. Now how we are trying to, so basically when you sort this array, let's say you want this output. You had this array 6, 5, 4, 3, 2, 1. You want to sort it in the ascending order and you want this output. This is your sorted array. Right. Minimum is predefined function. That's why we cannot have a variable named minimum. So let's say like this was your sorted array and this was your input array. So what we are trying to do is in every iteration, we are trying to place the correct element at its place. So we are starting from the minimum element. We are finding we find this minimum element. We place it at the first position. Then we try to find the second minimum element, which we will place here. So let's say you are trying to create a new array. So how will you create a new array from this, which will be a sorted array? We find the minimum element, we place it here. We delete this minimum element from this array. Then we find this, then we again find the minimum element in the input array, and we place it after this minimum element. Then we delete this minimum element from the input array. Right. Right. So so basically what this loop, in this loop we are trying to find the minimum element from index I to index n in the input array. This is our input array. Let's say you already declared a sorted array. So you can push your minimum element, whatever element you find in this array, and this will be your answer. Or either this, or what we can do is we can simply swap array of I with the element that is present at this index. So how will we like do this? We'll have to keep track of index also. I'll swap these two elements. Does this make sense? Is this clear to everybody? Is there anybody who has any doubts in this algorithm? Right. So what is the time right? So what is the time complexity for this algorithm? So this loop we know it runs from, so we know that this loop runs from 0 to n. So this is n. Now how, like this loop runs from I to n. What does this mean? So this means, so how we are going to calculate the time complexity? When my I is equal to 0, the inner loop runs n times. When my I is equal to 1, inner loop runs n minus 1 times. Similarly, n minus 2 times, n minus 3 times. So, and similarly, I goes till n. So, it will go till 1. So, 1 plus something, 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 something till n. So, we'll have some series like this of operations. Plus n. So, this is our time complexity. Right. So this is our time complexity. So when we sum this series, we get O of n square. So is there anybody who has any doubts in this algorithm?
Why you assigned idx equal to -1?
Sorry,
Line 12.
line 12. Why did I assign idx equal to -1?
Yes, ma'am.
So so this is like a flag. So let's say this minimum value that I had assigned to my variable, let's say that was the minimum, like there was no element smaller than this in this whole subarray, then my idx will be equal to -1. But I know for a fact that an array indexing starts from 0. I cannot have an index of -1. So I know that this was like the value that I assigned was wrong. So I can put a check here, check if my idx equal to -1, then like I made some mistake here. So this acts like a flag. You can put it anything, like anything will work. It does not matter. Even if you don't assign it here, it will work fine. Because for our use case, we have assumed that this is an integer, like all these elements in this array, the input array will be less than int max. But if they are greater than int max and I compare it with int max, then my algorithm will, then this algorithm will not work. Does that make sense?
Could you repeat it, ma'am?
1 second. Let me increase my volume if it is possible. Okay. So basically what I am saying is, let's say I had a variable. Now what will happen? This variable is there in the array. Now when I am trying to find the minimum element in this array, or let's say all the elements plus 3 int max plus 4, all the elements are greater than int max. Now when I am trying to find the minimum element in this array, I am comparing that, like I am comparing those elements against int max. Int max is smaller than all these elements. So function in place of JIDX is used. Yeah, sorry. So that's why we need this IDX. So we can put a check here also, like to check if this int max is like, if this was a valid assumption, if this was a valid comparison or not. Does this make sense?
Ma'am, what?
Sorry, I'm not able to hear. Is it like just
Got
me?
it, ma'am.
Can you increase your volume a little? Okay, so let's move forward. So the next algorithm is insertion sort. So how insertion sort works now is, so right now what we were trying to do is we were trying to uh, we were traversing the whole array. We were trying to find the element, the next element to put in the output array. What is int max? Int max is the maximum range of integers. So let's say you take 4-byte int, so it will be 2 to the power 31 minus 1, I guess. So So we were trying to find the next possible answer for the next possible index from the whole array. So we were traversing the whole array. Insertion sort is a little optimization over selection sort. So how this algorithm works is, so now let's say you had this out. So the concept is almost the same, but there is a slight trick. Bit of your volume. We are assigning int max values to array. We are not assigning int max values to array. Am I audible better now?
Yes, ma'am.
Yes, ma'am.
It's better now.
Okay. We are not assigning int max values to array. Okay, then I'll move forward with insertion sort. So what does the third line say? The third line says that these are 3 values in the input array. This is your input array. That's it. Forget about this int max. Let me take a big number. Let me take a big number. This is your number. That's it. This was just to take an example. You can forget about this. Let's look at the input array now. So let's say you have this array. Now you want to sort it using insertion sort. So what we did in selection sort was, we found the minimum element, we placed it at the correct index. We found the second minimum element, we placed it at the correct index. We are essentially going to do the same thing in insertion sort also. So we traverse this array, but how we proceed is, so in insertion sort, okay, let me show you an example. Right. Let's say this was the input array. Now we want to sort it using insertion sort. What insertion sort says is, insertion sort says that we'll keep the initial, let's say, so we'll keep some part of the array as sorted, and there will be some unsorted part. We'll we'll keep on iterating as we make the whole array sorted. So this is our invariant, that some initial part from 0 to I will always be sorted in the array, and this I will keep on increasing. So let's say this I is equal to 0. Is this subarray sorted in itself? Yes. This is just one element. One element is a sorted array. Now let's make I is equal to 2. I is equal to 1, sorry. Is this subarray sorted in itself? No. Why? Because 6, 5 is not sorted. So somehow we'll make this array sorted. Now we have 5, 6, 3, 4, 2, 1. Three, four, two, one. Now Now what we do is we make I is equal to 2. So is this subarray sorted in itself? No. 5, 6, 3 is not sorted. 3 has to be put before 5. So we'll make this 3, 5, 6, 4, 2, 1. Now this subarray is sorted from 0 to I, which is 2. 0, 1, 2. Now, but this subarray is not sorted. For I is equal to 1, this subarray is not sorted. For I is equal to 0, this subarray was not sorted. Does this make sense? Anybody who has who did not understand this part? Right. So, and how are we how will we basically sort this thing? How are we going to sort, how are we going to sort till I? So when I see an element, let's say 3, I know that the subarray before this element. So let's say I have an array. I see this element and I want to put it in its right place. This subarray before this element, this is sorted. This we know because we have maintained it. Sorted. So how we will do is we will compare this 3 with the element before this. Is 3 greater than this? If 3 is greater than this, then does this mean this array is sorted? Yes or no? Right. If 3 is smaller than this, we swap these two elements. Let's say I had a 6 here. So now I will have a 3 here and a 6 here. Now I will compare this 3 with this element. If this 3 is greater than this element, then this whole array is sorted, subarray is sorted. If this 3 is not greater than this element, if 3 is smaller than this element, then I'll swap these two elements and I'll keep going on like this until we put 3 at its right place. So this is how insertion sort works. So let's just go through the, can we use binary search for inserting element into the left part? Sakshi, you can use binary search to find it, but essentially it will not matter. So you will use, so so what you will do is you will use binary search to find the location where you want to put that element, right? Now let's say you got that location in log of n. Now when you want to actually put the element there, you have to shift all the element towards its right. So let's say you had x elements before x, you had to shift x elements. So you will be shifting x elements towards the right. Does that make sense? So let's go through the code for insertion sort. Sorry for that, guys.
Does this make sense? Right. So worst case, how many operations will we do? Worst case, for every I, let's say we start from I equal to 1. We'll go from j is equal to 0, so j is equal to 0. I is equal to 2. J is equal to 1 to 0. I is equal to 3. J is equal to 2 to 0. So basically, 1 operation, 2 operations, 3 operations, and so on. I is equal to n. J is equal to n to 0, n operations. So ultimately, we'll get this formula only, which will be O of n square, right? Best case, what will be the time complexity and when will the best case happen? So best case is when the array is already sorted, right? So then we'll only do n operations. We'll compare these two elements and we'll break. So in some cases, insertion sort works actually well if you have almost sorted input. So this was insertion sort, guys. Anybody has any questions?
You said we will do the half part once, and what about the next half part?
What do you mean by the next half part?
Like you said, we will do firstly we will do the half part will be sorted, and what about the another half part? Like,
No, Jada, we are not sorting, like we are not segregating based on the first half or the second half. We are saying as we move forward from 0 to I, I'll keep my array sorted. So what happens is when, let's say I equal to 0, so I just have one element in my subarray. So this subarray is sorted. When I is equal to 1, then I have two elements in my subarray, 6 and 5. Now I sort these two, 5, 6. When I is equal to 2, I have three elements, 6, 5, 3. So I sort these three, 3, 5, 6. This this subarray is unsorted now. Then I move I is equal to 3.
okay, ma'am, got it.
So then I sort these four elements.
Okay, got it, ma'am.
Okay. Um, let's move forward to the next algorithm then, which is counting sort. Um, so can you explain worst case time complexity again? So worst case time complexity is, yeah. So worst case time complexity is, let's say, so how do we find the time complexity is we just count the number of operations that we will be doing in total number of operations that we will be doing while these two for loops run. So when my I is equal to 1, my j runs from 0 to 0. So that is one operation. When my I is equal to 2, my j runs from 1 to 0, which is two operations. When my I is equal to 3, j runs from 2 to 0, three operations. Similarly, 4 operations, 5. So we'll get a series like this. These are the number of operations in total that we do in worst case. And that's how, like, when you sum this series, you get O of n square. Let's move to counting sort. Now guys, how counting sort works is counting sort works a little differently. So this is a sorting algorithm which is not comparison based sorting algorithm. Basically, we don't do comparisons in this sorting. So I'll not discuss this. Maybe we can discuss it some other time. So for comparison based sorting algorithms, the minimum time complexity that you will need is n log n. We saw two algorithms that this is the best case time complexity that you can get for a comparison based sorting algorithm. You cannot sort uh, like there is no time complexity better than n log n. If best case of n, that is for that is for a specific type of input. Like what if like that is not always true. We are not talking about a specific type of input here. So these are basically the number of comparisons that we need to do to find the right sorted array for any given input array. So we can get into the details some other time. But for we counting sort, this is not a sort. This is a sorting algorithm which does not make comparisons between the array elements. How that works is, let me just take an example. Right. Let me take a smaller example. It will be hard for me to keep track of elements. Right. Now, if I sort this input, I get 1, 1, 1, 2, 2, 2, 3, 3. So how counting sort works is, let's say I give you this input and I say that the maximum element is, let's say it's very small. Let's say the maximum element present in this input array is 10. Now what you can do is you can create an array. So basically, let's take this example. The maximum element, we find the maximum element present in this input array, which is 3. So I know there are and let's say all the like integers are positive. So I know there are just 3 integers. Like the maximum number of integers that there can be are 3 integers, 1, 2, 3. So I count the number of those integers. There are 3 ones, 3 twos, and 2 threes. I create an array. We have a 0th index also, that is fine. I create an array and I count how many ones are there. There are 3 ones, there are 3 twos, and there are 2 threes. Now what I do is I traverse this array sequentially and I create a new array out of these occurrences. So let's say there were 3 occurrences of 1. So I'll put 1 3 times. Then there were 3 occurrences of 2. So I'll put 2 3 times. Then there were 2 occurrences of 3. So I'll put 3 2 times. Does this make sense? Is there anybody who has any doubts in this? Right. So that's exactly how counting sort works. We count the number of elements. We do not compare, like I am not comparing here whether one is greater than two or two is greater than three. I just created an array. I count the occurrences of every element and I put those occurrences there and I traverse the array. I create my output array. That's how counting sort works. So, but the catch here is the maximum element. Basically, the number of elements that are there in your input array should not be a large number. So let's say n is equal to your size of input array. Then the range basically should be of the order of n. Only then the time complexity will be of the order of n. So basically our time complexity is of the order of range. So if this range is very large, then the time complexity will also increase. Is this clear to everybody? Any doubts?
Ma'am, can you explain that once again?
Which part do you have any doubt in, Tanya? Like, can you specifically ask the question?
What you just said, like the range should be, like how the range affects the time
Okay, you
complexity.
tell me, okay, let's take this input. Let's say the size of the input array is n. Let's forget about the range. Let's say the maximum element, okay, let's talk in terms of maximum element. What will be the time complexity for this algorithm?
Wait, what did you say about maximum element?
Forget about everything. Did you understand the algorithm?
Yeah, although I did have a doubt. When you're, like you said, there are no comparisons that are made, but like you're counting the number of occurrences of each like new kind of element that you see when you're traversing the array. But to put it into the new array in a sorted fashion, you would have to compare all those elements, right?
No, exactly. So we are not comparing any elements. That's what.
But then how would you know that you have to put all the ones
Array
first and
for
then
this.
the twos?
So let's say so when I create the array, let's say, let me remove this 3 and put a 4 here. So now I have, so I'll create an array like this. Agreed? This is my frequency array,
Okay.
right? Now I just traverse this array. Index 1 has a value of 3. It means the element, the number of occurrences of 1 is 3. 0 is less than 1 is less than 2 is less than 3. So the indexes are sorted. I am traversing on indexes. I don't need to compare anything now. Does this make sense?
No, I didn't get it. Wait,
Let
oh, so in this frequency array, what does that first zero represent?
so
Wait, so are you like, uh, so
let me
so if you had like 10 or something, you would basically have a lot of zeros in the middle, and then you would have
right.
number of occurrences of.
Exactly.
Okay.
Is this
Okay, so
clear now?
okay, but that would be like a huge array, right? If we have like big
Exactly.
values.
Exactly. So let's say you had a 10 here. Let's say you had a 20 here,
Right.
or some maximum element,
Okay.
right? Now, what is your time complexity? Can you tell me the time complexity for this input array?
So it would um
So we traverse this array once. Let's say the size of this array is n. So we traverse this array once, and then we traverse this array once, frequency array. So what is the size of the frequency array? The size of
okay,
frequency
it'll
array
be
is
equal to the
the maximum
maximum.
element.
Yeah.
So this is our time complexity.
Okay.
Now like it does not have to be this maximum element. Let's say the minimum element was not 1. It was not 2 also. Let's say the minimum element was 4.
Right.
So
Then it would be
basically we
maximum
can,
element minus 4.
right, exactly. So the minimum, so the range will be maximum element minus the minimum element basically. So if
Okay,
this
so if the
is
range is in the order of n, then
right, if the range is
it would
in
be
the order of
comparable.
n,
Okay.
then we'll have a time complexity of the order of n.
Okay, got
Large
it.
numbers in the array because it needs tree travel. Should waste a lot of memory for large numbers in the array. No, Tulika, we are like, if this range is small, then we are not wasting any memories, right? You can like, you can like initialize an array with this range and project all the whatever numbers are there to number minus minimum element. Is this clear to everybody? Let's look at the code for this. Does this make sense? No, it will be size of frequency array will. Yes, Pranav, and like you can like this is like the worst case where you can do maximum element plus 1, or if you want to optimize space, you can have max element minus min element also. So Jada, when you get this sort, now you have got the frequency for every element. So we just traverse the whole array. We find the occurrence of that element. So ith element occurs for um, these many number of times in our input array. So we put that, let's say I'll create, let's say this is my new array. Let's say this is my answer array basically. So what I'll do is I'll put that element that number of times in my answer array. I'll keep on pushing those elements in my answer array as I traverse the frequency array. Is this clear to everyone now? Is there anybody who has doubts in this?
Ma'am, could you please tell me how we use frequency of air array plus plus? I mean, what is the use of this?
So let's say like let's say my maximum element, let's say sorry, I initialize an array frequency which has size like this. So if this is my frequency array, then I can, for every element in array of I just need to increase the that will act as an index in frequency array. So let's say array of I is equal to 5. So let's I'll increase frequency of 5 by 1. Does this make sense? This will tell me how many number of times I have encountered 5 in input array. Frequency of 5 is the frequency of I denotes the number of occurrences of I in input array. Okay, let me write it like this.
Can you explain the while loop also?
We have all elements of yes. This is 0. Somebody was asking me something.
Yes, ma'am. Can you explain the while loop?
Sorry. Can you write down your question? While loop. Okay. So you need to put this element. So this is your element now. Do you understand this? What is your element? And how many times? So let's say this was my answer. I am at index 0. Frequency of 0 is 0. This occurrence is 0. I do not move inside. In I of 1, frequency of 1 is 3. So now my element, so now this is equal to, this is equal to 1 and occurrence is equal to 3. So this means that 1 has occurred 3 times in the input array. So since 1 has occurred 3 times in the input array and this is the smallest number available in the input array, so I'll put that number 3 times in my output array. How will I put it 3 times in my output array? I'll just keep on, like my j is equal to 0 initially, I put answer of 0 is equal to this, the number that is 1. I increment the counter, I put it again, like this loop runs for 3 times. Index is the element here. How can it be element be I? Because that's what we did, right? We count for every element. So what are you doing here? For every element, I am counting the number of occurrences those are there. So 1 has come 3 times in this input array. So that is why this 3 is there. So when I traverse this array, I know that this 3 represents and 1 has occurred 3 times in the input array. The time complexity of second for loop. Can you do a dry run for this code? Right. Now let's do a dry run for this code. The input is 111122, no 3 and 2 4s. 222 3203, right? Time complexity for second for loop means, do you mean this while loop? It will be max minus min. So if you,
Yeah, I mean, because for creating the frequency array, it's time complexity of n, right? So the other thing must be max minus min. Is it so?
so how
Because
So
if the
I
frequency
like
is
to
0,
do
then
it
it won't
is
enter the while loop, right?
don't look at the time complexity for this thing. So what I think you are trying to do is you are trying to like find the time complexity like the number of runs for this for loop and number of runs for this occurrences, right?
No, yeah, like for the whole thing in general.
Right,
Yeah,
exactly.
yeah,
So the
yeah.
whole for the whole thing in general is how many times does this loop run is the number of occurrences, the sum of number of occurrences in total in this frequency array, which is
Yeah.
basically 0 plus 3 plus 3 plus 0 plus 2, which is basically the number of elements that are there in the input array. So it's not max
The
minus
sum, you mean the sum of the element, sum of the frequency array.
sum of the frequency array, right? So it is not max minus min. Max minus min is the range. The number of elements could be very less, like very much less than the range.
Yeah. Okay.
So
Okay,
it
got
will
it.
be the number of elements, total number of elements that are present in the input array.
Yeah. Thanks.
Line 14, time complexity. Time complexity will be the number of elements that are there. And like, so this whole loop runs for the number of elements. We traverse this loop for frequency, and like this loop traverses all for the number of elements that are present in the input array. So this will be O of n plus range. Is there anybody else who has any doubts in this now? Or is it clear? Akash, you have some doubt?
Ma'am, max underscore ln, that is the size of the input array, right?
That is not the size of the input array. So for our case, max element is 4, the maximum element that is present in the input array.
Okay. Okay, got it.
Right. Dry run ones, okay. So for this implementation, it is not max minus min, it is max only. It is of range because I have not find the minimum element and I have not done all these projections. That will be difficult for people to follow. Yeah, so where were we? We were trying to do a dry run for this code, right? So this was our input array, this was our frequency array. So now what we want to do is so let me write the code completely, okay? This max element is equal to so this maximum element is equal to the maximum element that is present in the input array, which is 4. So I find this maximum element, which is 4. I initialize a frequency array, max element plus 1, and all the elements are initialized as 0. The syntax means that all the elements in frequency array are initialized as 0. There are 5 elements, 4 plus 1 is equal to 5. There are 5 elements and all the elements are initialized as 0. Now we go through this loop. What this loop does is
Ma'am, is there any reason behind adding +1 to the max element? Like when we initialize the frequency, so is there any reason why we added +1 there?
So basically, if you do this and you encounter your maximum element, can you access frequency of maximum element? Will that be in bounds for the array? No, right? That will be out of bounds for the array. So
Yeah. Okay.
So that's why we have to add a +1 here.
Okay. Right.
So for I is equal to 0, frequency array will look something like this. This is 0. This is 0. This is 1. For I is equal to 1, so what I did was the fourth index was incremented by 1. Here fourth index again was incremented by 1 because I found a 4 again. Now I found a 1, so I increment index 1 by 1. I found a 1 again, so I increment 1 by 1. I find a 2 and I increment index 2 by 1. Does this make sense? Akash?
Yes, ma'am.
Does this make sense now? So that's how you calculate the frequency. So once we have got the frequency, so this is how our final frequency array will look like. Now what we do, we traverse over this array. For I is equal to 0, this occurrence is equal to 0. So we'll not go inside this for loop. We can leave this. So I is equal to 1. This is 3. So this means that element 1 has appeared 3 times in the input array. So it has to appear 3 times in the answer also. So what we do, we go inside this while loop. We add 1 3 times into the answer. So how my answer look like is, this is how my answer looks like now. For I is equal to 2, 3 times element 2 has appeared. This is how my answer looks like now. There is no 3 present in the input array. There are 2 4s. This is how the answer will look like finally. Does this make sense now?
Yes, ma'am.
Is there anybody who has any doubts for this?
Once repeat the time complexity part of the while loop.
Time complexity remains the same. The algorithm that we are following, like this is just so how we calculate the time complexity for this is, so this loop, basically the outer for loop, runs for the frequency array, like the number of elements that are present in the frequency array, which is in our case the total, like the maximum element present in the input array. And this while loop basically runs total number of input array, the total number of elements that are present in the input array. The while loop runs for these many number of times, the total number of elements that are present in the input array. So time complexity is of size of input array plus the maximum element that is present in the input array. Does this make sense to everybody? Right, let's move forward.
One last doubt.
Yeah.
So the only disadvantage is if the maximum element is too big, then the frequency.
Then you cannot use this algorithm, yes.
Because the frequency array will be too
Correct.
big. Okay.
So let's say the input size was 10, but the maximum element that was present in the input array was 100. So basically your n was 10, but the maximum element was n square. So the ultimately time complexity that you are getting is O of n square.
Yeah, but can we like just check if it's not, if it's 0, then just skip it or something for it
0 as in what is 0?
If the frequency is 0.
Frequency is 0. If the element is there, then it means the frequency is at least 1, right?
No, I mean like for a sparse array, like if the maximum is 100, then you'll have a lot of zeros in the frequency array, right? Okay, so let's just say like 441100 or something.
Okay.
So you'll have a lot of zeros in the
Correct.
frequency. So while in the second for loop, like while traversing the frequency array, you can just ignore the elements which are 0, right? How will we
But
get it?
how will you know which elements are 0? You will not know,
You'll
right?
have to
So
compare it.
Correct. So another way of doing it is, but that is essentially not a counting sort algorithm, so we can leave that. That's fine. If we do that, that is n log n essentially. No, that is n log n. It's okay. We can leave that. Yeah, that is n log n. So yeah, you can't do that because then you'll be comparing basically which elements are there, which elements are not there. You'll be keeping a set kind of thing where you will store these elements are present, and like if you will do those lookups, it will essentially take time.
Yeah.
So this is there. Let's solve one question for this. Guys, just go through this question. This is a question based on counting sort. Then we'll look at the code for this question. Has everybody read the question? Right. So what this question says is you are given an array of 3 colors, 0, 1, and 2. You just need to sort those colors. That's it. That's what we want to do in this array, in this algorithm. So we are going to use counting sort for this. No, size of colors can be 3 because we just have 0, 1, and 2. We don't have a 3. So this is our algorithm. Is this clear to everyone? Is there anyone who has any doubt in this question? This is like the exact same, just the implementation of whatever we discussed till now.
Ma'am,
Yeah.
there is just one doubt. I mean, in this array, basically we already know that the maximum element is 2. So that's why you make a size of vector 3. That is max
Correct.
element plus 1. Otherwise,
Correct.
we find the max element, then the size of vector will be max element plus 1.
Correct. What algorithm does libraries sort function use? It's a hybrid of so basically for larger size inputs it uses quicksort. When quicksort does not perform very well, it switches to heap sort, and for very smaller inputs it uses insertion sort. So the algorithm is called intro sort. It is a hybrid of these three algorithms.
Ma'am, how to do the question in one pass?
That is a two-pointer algorithm. Are you guys familiar with two pointers?
Yes, ma'am.
Yes, ma'am.
So I think then like you guys can suggest how can we do this in two pointer in one pass. So suggestions, ideas? So basically I'll give you a hint. So what we want to do is we want to put all zeros in the front and all twos in the last. If we do this, all zeros are in the front part of the array and all twos are in the last part of the array, the array is sorted. We have to divide this array in three parts somehow. Ideas?
Ma'am, is this that Dutch flowers
Yeah,
algorithm or something
yeah,
like
it's
that?
that only.
I don't remember it properly, but I remember seeing a question like this.
I think you guys can take it up as a homework question and maybe work it out. It's a good problem actually. It's a good two-pointer problem. That's why this is a medium question. Otherwise, if you just have to implement counting sort, it would be too easy. Kind of, Gaurav, yeah. Like, let's say I'll give you just a hint of kind of what happens. So let's say you have a pointer at the starting, you have a pointer at the end. So you see this 2 at the left pointer and you see 0 at the right pointer. Now we know that we want to put 2's in the last and zeros in the front. So ideally, in the ideal scenario, I should get all zeros on the left pointer and 2's on the right pointer. Basically, either I'll have both 2 on left and right pointer or I'll have 0 on left and right pointer. I cannot have this case. This case can only be when the input is not sorted. So I can swap these two elements. I can like if I swap these two elements, then I have to sort this array only. and I can move my pointers accordingly. Does this make sense? Now what happens when I like encounter a 1? I don't know where to move, or do I? So in this case, if you have a 0 and a 1, you know this 1 could be in the right position, but this 0 is definitely in the right position, because whatever 2s or whatever 1s we had like encountered before this 0, we have moved those towards the right. Does this make sense? Is this making any sense? Do we want to solve this problem right now, or do we want to move forward? Right, let's move forward. So, there is another algorithm called bucket sort. +1, could you repeat that? Because if you don't do a +1, then you cannot access maximum element in the frequency array. It will give you an out of bound error. So let's talk about bucket sort, how bucket sort works. I'll not like go through this algorithm in detail. I just give you an idea. So how this algorithm works is, so let's say so let's say this is roughly how my input looks like. This is sorted right now. Let's just assume that this is not sorted. Now, what if I want to sort this using counting sort? Count sort. What happens is I create an array of size 100. I create an array of size 100. I count the frequency of every element, and then I put then I traverse over the frequency array, and I put the elements in the sorted array. Time complexity for that solution will be T of 100. Basically 100 operations. I am doing 100 operations while traversing over this frequency array. A better solution could be, I could divide these elements. Let's say we just have 10 elements. Let's just take 10 elements. Approximately 10. It's fine. This will work. So let's say we just have all, like, this is very small number of elements. I think 13, 14 elements are there maximum. To sort an array of 13, 14 elements, we are doing 100 plus operations, which is not very good. So what we want to do right now is, we'll see how bucket sort works. How bucket sort works is, bucket sort says that you divide your input array into buckets of equal sizes. So let's say this was the range for my input array, 0 to maximum element. What I'll do is, or let me take minimum element. What I'll do is, I'll divide this range into buckets of equal size. For this, let's say we take this as the example. For us, very convenient bucket size would be 10. So how many buckets will be there? 10 buckets will be there. So I have 10 buckets. What does each bucket represent? Each bucket represents a range, a smaller range. So from 0 to 10, or I'll say 1 to 10 is one range. 2 to 10, 11 to 20 is another. So I have these 10 ranges, 1 to 10, 11 to 20, 21 to 30, 31 to 40, 41 to 50, similarly 91 to 100. So I have these 10 buckets basically. Now what I'll do is I'll put these n elements, the size of the input array is n. I'll put this n elements into these 10 buckets. How I'll do this is I'll just check every element which bucket it falls into. This one falls into 1 to 10. I'll put this one here. 10 falls into 1 to 10. I'll put this 10 here. 22 falls into this 21 to 30. I'll put this 22 here. This 33 falls into this bucket. Let's say there was a 34, so this 34 will fall into this bucket. Similarly, I'll have 95, 96 and 100 in this bucket. Does this make sense to everybody till now? What we are doing? Is there anybody who does not understand this segregation into buckets? So now we have divided our input, which was of size n, into these buckets. Let's say insertion into, let's say like the finding of this bucket is O of 1 is constant time. Insertion into the buckets is also constant time. So the time taken to put all these elements into the relevant buckets is O of n. There are n elements. Now what we will do is we will sort the respective buckets. These buckets I will sort. And now let's say I have sorted all these buckets. Somehow, I used some algorithm to sort these buckets, and now these buckets are sorted. So I list down the steps here. This is O of n. This we will see. Now I traverse over all these buckets and I create an output array. So how many elements are there in total in all of these buckets? N elements. So basically when I put those elements together, it will essentially take traversing all these buckets, which means traversing all these elements. This step is very similar to what we did for counting sort while getting all the elements from frequency array. Everyone with me till here? Is how many people are lost? Right. So now the only step that remains is how do we sort all these buckets? So how do we sort these buckets is we can use counting sort for that. Basically any algorithm which is not a comparison based sorting algorithm. No merge sort, no quick sort, as long as you. So for our sake, we'll always use counting sort. So if you use counting sort for this, so now we talk about the overall time complexity. So the time complexity for this step is average case of n if we use counting sort for all the buckets, and we say that the elements were like uniformly distributed. If the elements were not uniformly distributed, basically all the elements were from this bucket, then our algorithm will not work. Then this bucket sort algorithm basically will take time equal to counting sort, which will be O of n square in this case. so it will not work. But if the elements are uniformly distributed among all the buckets, then basically for every bucket what we will be doing is, let's say so for every bucket, the average case, if we sort every bucket using counting sort, the average case time complexity will be O of n. The proof for that is very tricky and very difficult, so I will not get into the proof. It involves a lot of mathematics. Yes, Shashank?
But like, if you look at the last bucket, right? If you use counting sort for that, won't it take 100 time steps to do it?
For last bucket, it will take these are 5 elements, 6 elements.
But the maximum element is 100, right? So, okay, like because the frequency array will be 100 length for this.
No. So for this, yes. So in this case, we are assuming that for counting sort, frequency array will be of size max minus min. That's how we have to implement counting sort.
Oh, okay.
We cannot initialize the counting sort array with max plus 1. If we do that, then there is no point of using bucket sort. If you guys want me to code that solution also for counting sort, we can do that also. So this is how basically bucket sort works. Do you guys want me to code that solution for counting sort, max minus min plus 1? How many people want it and how many people wanted to take it as a homework? I think it will be better to take it as a homework. No is for home, right? What is this no for? Okay, yeah. Right. So this was bucket sort for you. Next, we'll go through some custom comparator and how we use. So this is clear for everybody, right? So right till now we have seen selection sort, insertion sort, counting sort, and bucket sort. Is this clear? Are these 4 algorithms clear to everybody? So yeah, so let's move forward. Then finding max and min among the input would be O of n. That's a simple way to. Okay, so let's take this question also. This I think everybody should know. So can you find maximum or minimum in an array in less than n operations?
Ma'am, we can use star max underscore element. Like we'll start from the like if there is any vector present, then from
and what
like
is the
say. Sorry.
What is the time? What is the time complexity for that?
Ma'am, n O of n.
Correct. So my question is, can we do it in less than n operations?
Like there is a command for in STL, right? Underscore asterisk max underscore element.
Correct. So when I say that can we do it in less than n operations is can we do it in less than O of n time?
Okay.
It's not about the command you use. It's about the algorithm and the time complexity for that algorithm. So we cannot do this. So let's say I will prove this. How I will prove this is, so let's say you want to find the maximum in an array. So what you will do is, so let's say you had these are my n elements. Now I do not, so to find the maximum element, how I compare is which one is greater, A and B. I compare A, B, B, C, C, D, D, E, F. Basically, maximum till now with E, maximum till now with F, and so on. So I make n minus 1 comparisons in total. Now, can I do it in less than n minus 1 comparisons? No, because then I will be leaving out one number at least. If I am doing less than n minus 1 comparisons, I am at least leaving out one element which I am not comparing it with my output. What if that is the maximum or the minimum element? So you cannot do it in less than n minus 1 operations. Is it clear to everybody? Right. So now we'll look at how do we use STL sorting library for like coding purposes. So whenever you will be solving questions, you will rarely be writing your own sorting algorithms. You will always use this STL library. Very rarely it will happen that you will want to write your own sorting logic. You will want to write your own sorting algorithm, which might happen in case of counting sort, which might happen in case you want to write like bucket sort or something else. Otherwise, you will always use this library. This is std sort. This is the algorithm that we are talking about. But not so. This algorithm takes is, it takes two iterators. So this is how you can use this algorithm for any, let's say, so I'll show you the syntax. So let's say this was my vector. So this will be my starting iterator. This will be my end iterator, and this sorting algorithm by default sorts this vector into ascending order. What if I want to sort this vector into descending order? What if I don't have a vector of integers? What if I have a vector of some class objects? I have a custom class. And I create a vector of that. Let me call this class a matrix. But if I want to sort this vector now, how do I do this using this sorting, this library? What if, let's say I have a vector of pair. Then how does this algorithm, then how does this library work, and how will it sort? Like, will it be based on the first value? Will it be based on the second value? How do I ensure that, like, if I want to sort it in a certain way, how do I get my desired output? So this library takes a third input, which is a comparator function. What does this mean, a comparator function? This means that you can dictate how you want your input to be sorted. So this is what it means. Now this comparator function can be a lot of things. It can be a lambda, it can be a functor, it can be a function pointer, it can be anything. So let's see how we implement it using, let's start from a function pointer. So let me take an example. What does this piece of code mean? So this means I have a function which takes two inputs and it returns me if a is greater than b, it returns me true. If a is less than b or equal to b, it returns me false. How does this function, if I write the function name here, what does this mean? This means that you are passing a function pointer, a pointer to this function, to this library. Now, how does that work is what this library will do, what this library does internally, it will iterate over this array. It will compare, let's say, this was your input array. If this was your V, what this library will do is, let's say it has to compare 2 and 3. This library does not know whether you want to put 2 before 3 or you want to put 3 before 2. So what it will do is, if it wants to know the sequence for these two elements, it will pass these two elements to this function 2 and 3. If you want to put A before B, then it has to return true. That means when A is greater than B, A will be put before B. So finally, this library will sort the input in descending order based on this function. Does this make sense to everyone? How many people are lost? Who did not understand this?
Ma'am, that vector pair int thing that you've written, is that relevant right now?
No, this whole thing is not relevant. This whole thing was to make you understand the purpose of this parameter. Why do we want this parameter? We will see more examples. As we will see more examples, we'll appreciate how this whole thing works.
Also, that pair int thing, is that like a standard way of writing it? Like, do you write, like, is
Yeah.
pair like a standard word you use?
Yes. This is a C++ container. This is a C++ library again.
Okay.
You can ignore this for now.
Okay.
Let's ignore these three things for now. Let's just look at this piece of code. Akash, which part do you want? Like, what did you not understand? Tell me that. Or what did you understand? Let's say I give you this array, or not this array. 3, 4, 1, 2. I give you this array to sort. Now what happens? Like, how does this code works? What did you understand? Depends, Sakshi. You can use it. Like, you just like this, whatever function name, whatever functor you pass here, that should be valid in your scope. That's it. It's fine. Yeah. We'll take more examples, Pranav. So in C++11, that is just for, this is just for people who understand C++11, others can easily ignore. So
Excuse me, ma'am.
yeah,
Ma'am, whenever we use this sort function, we generally take sort of b dot begin and b dot end. We don't use generally compare function.
correct.
Why it is so?
Because generally we need the output to be sorted in ascending order.
So
If you just do this, this will sort this vector in ascending order, 1, 2, 3, 4, 5. That's what you will get. What if you want 5, 4, 3, 2, 1? Does this make sense now?
Can you explain, like, give a dry run of the descending order thing?
Descending order thing. So I'll show something. So the example that we took we had a 3, 4, 1, 2, and 5, right? So how comparison based sorting algorithm will work is, so let's say I first compare. So what does it mean to sort? I have a 3, 4, 1, 2, and 5. What does it mean to sort an input array? It means that if I permute this array somehow, I should get this permutation. 1, 2, 3, 4, 5. So what will be the worst sorting algorithm existing in the world? I take all the permutations of this array and I find the permutation which has all the numbers in the ascending order. Does this make sense to everyone? Is there anyone who does not understand this statement? How do I find the sorted permutation of an array? I find all the permutations of the array. I take out the sorted one. This will have a very bad complexity, but this is one algorithm. This is what sorting an array means. This is what we are essentially trying to achieve. We are trying to achieve a permutation of the array which has all the elements sorted without actually finding all the permutations. So now when we are talking about finding permutations, we are talking about putting a sequence on these numbers. So let's say I say I want to sort this array in ascending order. Now I don't know whether 3 has to be placed before 4 or 3 has to be placed after 4. So what I'll do is I'll compare. If 3 is less than 4, then I'll create a then I'll compare other elements. If 3 is greater than 4, if 3 is greater than 4, then I'll follow this route. I have two routes. Either 3 is less than 4 or either 3 is greater than 4. Let's say we have just 3 elements. Let's not take 5 elements. That will be a very big tree. Now I'll compare 3 with 1. If 3 is less than 1, I'll go here. If 3 is greater than 1, I'll go here. So this branch means 3 is less than 4. This branch means 3 is greater than 1. Now I compare 4 with 1. 4 is less than 1. So this branch means 4 is greater than 1. Now based on these results, I decide that this is my desired permutation. If this was true, that is if this was true, let's say 3 is less than 1. In some parallel universe, this is true. 3 is less than 1. In some parallel universe, this is true. So I have 3 less than 4. I have 3 less than 1. So my minimum element in the array is 3 now. Does this make sense to everybody? Is there anybody who does not understand this statement? In a parallel universe, if 3 is less than 1, the minimum element between 1, 3 and 4 is 3. Now I have to compare 1 and 4. Let's say in some parallel universe, 4 is less than 1. So my second minimum element will be 4. So this will be my sorting. If these branches, like if these branches were true, if 3 is less than 1, if 4 is less than 1. So that's basically how we achieve our sorting. So now going back. So what this algorithm does is this creates this tree. It compares this 3 with 4, then it will compare 4 with 1, then it will compare 3 with 1. Let's just take the smaller example, 3, 4, 1. So it compares 3 with 4, it compares 4 with 1, it compares 3 with 1. Whatever combination permutations are there, it will compare all these elements, okay? Based on these results, whether 3 is less than 4 or greater than 4, it decides what to put first. Now, when we use this function, it does exactly the same thing. It just uses this function to compare which element to put first. That's what this function is doing. If it returns true, it means we put A first. If it returns false, we put B first. Does this make sense now? So when we say we want to sort an array in decreasing order. If the element, if A is greater than B, we want to put A first. That's what descending order means. If 4 is greater than 3, put 4 first in the output. That's what we are doing here. That's what we are returning true here. Anybody, any doubts?
Ma'am, what is the time complexity of this sort function?
N log n. Clear?
Ma'am, once the like you said, like all possible pairs of elements from the array will be sent to that compare function, right?
Not exactly all the pairs, but so it's like so I'll give you this example.
No, like wait, basically before that, I wanted to ask. So once you compare the two elements, it sends either true or false. Then what happens? Like, what does it do?
So you will have a better understanding when we go through the recursive algorithms. What happens, like how merge sort works, how quick sort works. So basically what is happening here is, basically what is happening here is when we go here, so let's say it is trying to find the minimum element. While going through this, let's say we are trying to use insertion sort here. Somehow we are trying to implement those operations. Then somehow we are trying to find the minimum element. By using this set of operations, we found the minimum element. Then we will do another set of comparisons to find the next minimum element. That's what we did in selection sort, right? Let's say we create a tree for selection sort. How will we do that? Is it making it any better? Does this answer your question?
No, ma'am. Wait, you said selection. You said insertion sort, and then you said
Let's say we take the example of selection sort. Okay.
Okay.
How selection sort works is we want to find the minimum element in this array. Right. So what we do is we compare 3 and 4. We found that our minimum element between these two is 3. So we come here. Now we compare our minimum element 3 with 1. 3
But
less than 1.
this is
If
insertion sort, right?
no, I am just talking about finding the minimum element. This is selection sort right now.
Oh, okay.
Right. So we compare 3 with 4. if 3 is less than 4, basically this is index 1, this is 2, this is 3, this is 4, this is 5. So what we are doing is we are comparing index 1 with index 2. If index 1 is smaller, we come here. If index 1 is larger, we come here. Now, if index 1 is larger, then we compare index 2, A of 2 with A of 3. If index 1 is smaller, then we compare index 1, A of 1 with A of 3. Does this make sense?
Right.
Right? If we go by this route, at the end, after n minus 1 operations, I will have the minimum element that I want to find.
Okay.
Now that is 1. Now what I will do, I will make more operations. I will do more comparisons. I will compare this element again with A of 1, A of 2, A of 3. Basically, I will again compare. Like basically, what we are doing is we are comparing, right? Whatever comparisons you are doing, you are just doing like, let's keep doing those comparisons in like a tree sort of fashion. Does this make sense?
So after you found one, then the rest of the numbers you'll do the same thing. That's what it is.
Sorry?
After you found one,
Right.
like you found the first minimum element,
Right.
then the rest of the array you'll do the same thing to find the next minimum
Correct.
element. That's what you're saying, right?
Correct.
Okay.
Correct. So we are just making all those operations. So basically in this like selection sort, you are doing n square operations. In some optimized algorithm, you will be doing n log n operations. That's what it means.
Okay. Okay.
So that's how when we are doing these operations, that's how it is keeping track. Somehow it is keeping track of like the permutation. Does this make sense now?
Ma'am, is it like for writing in descending order, we are giving as compare function also in line 7?
So there is an inbuilt operator or an inbuilt comparator function for descending order. This is greater of it. Like if you just give this function, then it will sort the input in the descending order. So we don't really need to write a custom operator for this. But let's say I had a struct it had two elements, x and y. And I create a vector of these elements. Now, if I try to sort on this vector, will it be able to sort on this? Like, will it be able to sort? Hello, is it audible now?
Yes, ma'am.
So if I want to sort on this struct now, will it be able to sort? No, right? It won't be able to sort. How will it sort? How will it know whether you want to sort on x or y? It doesn't know whether you want to sort on x or y. So you will have to provide this library with a way for it to know which parameter or which field you want to sort this function on. So basically the arguments to this function will be the type of vector element. So every element in a vector is of type node. So we'll be comparing two nodes. We'll tell this library how to compare two nodes. It can only sort the like defined STL containers or STL like basic data types, defined STL containers only. Yes. Default is A less than B. How do you define A less than B? Less than is not defined for this struct, right? That's what we want to do. We want to define less than b for a struct. This less than b operation is not defined for a struct. You can't compare. How will you compare to? So basically, if I write node a comma b, and if I try to compare if a is less than b, is this operation defined? This operation is not defined for a struct. So for custom objects, we have to like either you, so what you can do is either you can overload this operator, not struct. Okay. So for int, this is a less than b, yes. Yes. So either what we can do is we can do this or we can do this also. Like anything is fine. This is your way. However you want it, whatever way you want it. Everything is fine. If I want to check a dot x greater than b dot y, that is also fine. This is what I wish to do. If this is what you want to do. So, but you need to define this comparator function, or you can define the less than operator in your for your struct. That is called operator overloading. Let's not go into that. So is this clear to everyone for a custom object? Time complexity, Akash, you can just like for now you can just memorize it. It will be O of n log n. These are recursive sorting algorithms that we'll be covering in the next class. Just not for descending order, for comparing any two objects. If you do not want to sort your, if you either you do not have if you don't, let's say you are, if the objects that you are trying to sort are not custom objects, those are already defined in C++ library, let's say, but you do not want them to be sorted in ascending order, or you want them to be sorted according to some function, like according to not like whatever default library provides you, then you need to write this compare function. Or if you have custom objects, then you need to write this compare function. It's not like I cannot sort in ascending order using this function. I can use this function to sort in ascending order also. N log n is what you get when you like sort using quicksort. That's why this algorithm uses quicksort and heap sort. That's what those two algorithms provide you. N log n. That's how it runs in N log n. Greater than or less than operation is not defined for custom objects, Tulika. You need to either define those operations for your custom classes or custom struct. Otherwise, you cannot use this. A greater than B means nothing, like this code will not compile A greater than B. The compiler does not know greater than operation for custom objects. Is this clear, guys? Do we want more questions? Does this make sense? Why we have this function and how are we going to use this function? Now there are different syntaxes how we can like create our custom comparator. This was one syntax that we saw right now. There is another syntax. So either I can create a struct or I can create a class. don't get confused with this const. Like you can remove it. I just have the habit of writing the const while writing the comparator functions. It's a good habit. So again, so I define this struct and I define this function. This function has to be named exactly like this. And this, when while sorting this array, this library will call this function, this operator with parenthesis function. How it does is basically this function again acts like a functor. This basically this word here means it is a functor of this struct and it calls this operator function. That's it. That's what it means. Let's not get into this. Is a dot x for referring to struct? Yes, that's how you will. So basically these variables. So there is a there is a concept of private and public variables in struct and classes. By default, all variables in struct are public. So whenever you have a public variable, you can just do object dot like whatever variable name there is. So a dot x will work. Like if this was a node, and I want to sort it on x, then I can do a dot x less than b dot x. Oops, objects. What is a functor? Functor is like we can let's not get into that. Those are like high level C++ concepts. Let's not get into that. So this just means that you are referring to this function of this struct. That's what it means. Let's cover this functor concept in your like OOPS or maybe some other C++ class. That will be better. Otherwise, people will get lost here. Apart from this functor concept, is this thing clear to everyone? Like this will be the syntax, guys. This will be the syntax. How it works is what a functor is. Let's not get into that. You will only get confused. What do you mean, Karan? I did not get your question. Why do you want a comparison function inside your struct?
Why are we putting the whole thing in a structure like the compare function?
So that is just another syntax of how you can do it. Basically that function. So you might see the syntax in a lot of places. So I just wanted you to know this syntax, that this is how also you can write it. There is like, this is another way of writing custom comparator. That's it. For normal use cases, like just do it with a function. So there is another way of writing it is using a lambda function, which I generally never use. because I don't write it. I don't like the syntax of it, and the code becomes really messy and harder to read. So I will not I will not want anybody to use lambda functions per se. But so what a lambda function is? A lambda function uh, is an anonymous function. That's it. A lambda function is an anonymous function. So basically what you do is you write your function here itself. Here. You don't give a variable name, you don't give an object here, you just write your function here somehow. Let's say this is how you will write your function here. So how we do it is this is how it works. That's it. I just write my function here. That's how a lambda function works. This is just another syntax. Does this make sense, guys? Everyone with me till here? Who doubts? Excuse me. Is this the no? This is not the return type. So while writing lambdas, like if you want to pass some input to the function, so this is like the um, so this is like passing the variables. So these are like your arguments. But if you want to let's say I had a map in the function and I want to pass that map and I want to use that map here. I just cannot pass it in these two arguments, right? Because then this operator will not this will not be a comparison function. So I have to pass it here. Some parameters, some variables or some objects that I want to use inside the function. So Akash, I personally never used a lambda function. If I have to use a comparator, I will write either like this struct or I will write a function. I never use a lambda function. These are too complicated and makes the code very ugly. So let's solve a question. Yes, Karan, you can do that. So basically, you don't basically the algorithm does not care whether you are like writing a begin or an end. It just needs two iterators, whatever iterators you want to give. So you can give begin plus 5, or if you have an array, you can give a plus 5. That is like that will act as an iterator. So guys, this is a question where we have to sort this array 1 based on array 2. Just go through this question and then we can look at the implementation for this question. Guys, ideas how like the implementation, like what will be the algorithm for this question? How will we do this? How will we use counting sort, Rahul, for this question? Guys, just unmute yourself and like speak the algorithm. Rahul? Okay, so let me just explain the question for everybody right now. So guys, the question is you are given two arrays. Based on array 2, you have to sort array 1. What does this mean? Based on array 2, you have to sort array 1 is if in array 2, element 2 comes before element 1 in array 2, then in array 1, element 2 has to come before element 1 while in while sorted. So this 3 comes after 1 and 2 in array 2, then this 3 come after 1 and 2 in array 1 when we have sorted the array. So this is what it means. Now the question says that all the elements of array 2 are distinct and they are present in array 1, but there are some elements in array 1 which are not present in array 2. Those have to be listed at the end in sorted order, in normal ascending order. That's what the question says. Yes, guys. Counting sort till max element of array 2. What does this mean? Okay, so I think nobody wants to say anything, so I'll just go through the solution. So the solution is right, Sakshi. So one way of doing this is using counting sort, count all the elements that are there in count the occurrences of all the elements in array 1 that are present in array 2. Go through array 2, find the frequency of every element, put it in the output array, and whatever elements are remaining, sort them and put it in the output array. That is one algorithm, or we can use a custom operator for this. How will we use custom operator for this? Let's see. So what this function does is, so we have created this map of where every element in array 2, no, I have to define this function. So we have created this map of every element in array 2 occurs at I. So let's say I have put it in, so let's say I have some magic function which tells me these indexes. So this is present will tell me if, oh shit, yeah, sorry, my bad. Yeah. So basically what happens is we check whether these two elements are present in array 2. If these two elements are present in array 2, we check which of them occurs first. So let's say index at which A occurs is smaller than index at which B occurs. Then we return true, otherwise this function returns false. Now let's say B is not present in array 2, but A is present in array 2. So we return true. Basically all the elements that occur that are present in array 2 have to appear before all the elements that are not present in array 2. That's why we return true here. If A is not present but B is present, we return false, which means we want to put B before A.
if both are not present, we want to put them in the sorted order. A is less than B. Does this make sense? And this is present function, you like people who do not understand math can take it as a black box.
So this is just to check the indexes of every element in array 2. That's it. So what happens now is if I have two integers, what I do is I check if both of them are present in array 2, I check which of them appears first. So let's say if I am comparing this 2 and 1, the index of 2 is 0, 1 is 1. So if both of them are present, 2 and 1, let's take this example. No, actually it's a very bad example. So let's just take this, what, 4 and 3, 3 and 9. Let's take 3 and 9. Okay. Let's take 3 and 9 so that it is less confusing. So element 3 is at index 0, 1, 2, 3. Element 9 is at index 4. So both of them are present. Now if I am comparing these two elements using this function here, this 3 and 9, what I'll check is the index of 3, index of 9 in array 2. Index of 3 comes before index of 9. So I return true. Otherwise I would have returned false. Let's say now if I am comparing 3 and let's say if I am comparing 3 and 19. 19 is not present in array 2. That's why I want to put 3 before 19. So I return true. Now let's say if I'm comparing 19 and 3. Now 19 is not present. So my A is not present. So I return B because I want to put 3 before 19. So I return false. Now let's say if I am comparing 7 and 19. Both of them are not present in array 2. So I return A less than B. Does this make sense now? Wrong answer. True, false. All right. Guys, in lead code, if you ever create global variables, do uninitialize them, like initialize them basically. Clear all those variables in the starting of the function. Otherwise, it will create a problem like when there are multiple tests. And you will get wrong answer. So this is very important. So I think that's it. So like we covered selection sort, we covered insertion sort, then we covered counting sort, bucket sort. We learned how to write custom comparator for STL sort. Now there are certain problems that I have. I think I don't know about, can't we just do it only by using just function? So basically, Akash, the thing is you can do it using the function, but how will you know which element to put first? So basically you will go inside this function and you will check what is present. So is present, just check whether this element is present in array 2 or not. You can take it as a black box. Just leave it. You can take it as a black box. Just think that this is present, checks whether this element, this A, is present in array 2 or not. That's what it does. Somehow, magic. That's what it does. It checks whether A is present in array 2 or not. If it is present in array 2, this indexes of A give me the index of that element. This is just an optimized way of doing this. That's it. Does it make sense? Otherwise, I will have to iterate over the whole array 2 and find the index of this element. Or we can, yeah.
For the comparing between A and B, we need to consider all possible permutations for combinations to like write the code, right? Like
So we are not comparing between A and B. We are comparing in A itself. A itself based on B. That's why we need this function. Whether this element is present in array 2 or not. We are not comparing like in. So both of these elements are in A. We are just sorting this array 1. It has nothing to do with array 2. This logic is custom.
Why we use indices dot clear?
Sorry.
Indexes dot clear. When you define the global variable and use indices dot clear.
So it means like before running this function, this line means that there are no entries in my map. So what it does in between, so what LeetCode does is if it runs like 10 tests simultaneously and you have global variables, so some data from the previous test could still be present in your variables. So that's why we need to do it here. Any questions, guys? चमका या उड़ गया? तो यार यहाँ क्या हो रहा है, ये इसको ब्लैक बॉक्स की तरह लो. Just forget about this. Forget this map is there. Forget this map is there. Okay. I am going to write a code which will not work if you submit it. Okay. Yes, Tulika. Does this make sense now? एक index, we have a vector called indexes. We have initialized with a large memory. Now what I do is at every index of this array 2 of I have stored the index at which this element occurs. Now in my custom comparator, what I do is I check if this element occurs in array 2. How do I check is index is not equal to -1. If the index is not equal to -1, uh, I access that index and I compare the two indexes. Does it make sense now? अब किसको नहीं समझा? ये कोड किसको नहीं समझा? So this code will work for smaller use cases where like maximum element in array 2 does not is not greater than these many number of elements. Otherwise, again, we'll have to find the maximum element and then we'll have to uh, create our array according to that. If the maximum element is very big, then we cannot use a vector. I just ran it. I'll just submit it. I don't know if it will work. What is the maximum element? So, array yaar, I did know. If indexes of element is not equal to -1, return true. Is not equal to -1, return true, else return false. Is not present. अच्छा हाँ, it is not this. It is fill of indexes. Again. Yeah, I did a clear here. I don't know why it is not working. Is it something to do with the initialization? I think it has something to do with the initialization. Right. So apparently, yeah, I cannot like initialize global variables like I did. I cannot just initialize this vector here. I have to initialize it inside the function. So does this make sense? Now this is clear, right? This is a vector. Now we know how we are like using this is present function, how we are using this compare function and all. Is this clear, guys? Right. So guys, I think that's it for today. I think this was a long